everything we've covered in this class so far, for example, we started with cubics and quadratics. We focused more on quadratics though. And quadratics are basically a polynomial where the degree is 2. So it's like x squared plus some other stuff, but it's the degree of 2. Then we went to polynomials where we had degrees of 4 and 3 and 5 and 6 and all this other stuff. Rationals are basically the same thing as polynomials, only we're taking a polynomial and we're dividing it by another polynomial. Okay? So instead of just regular polynomials like we've had, now we're dividing them. That's what a rational expression is, essentially, a polynomial divided by another polynomial. Okay, here is the breakdown of the full unit, but it's actually nothing different than what we've already done. Okay, we've done factoring, we've solved polynomials. Now we're just dividing polynomials, essentially, and that's what a rational expression is. Here is a review from, and don't write this down because I just want your brains for right now. When I'm actually writing stuff down, that's what you're probably going to want to write it down, or if I specifically say, hey, write this down. But this stuff we've already covered, so there's no reason to write this down for right now. Okay, polynomial expressions. By the way, if you do want to write it down and I'm going too fast, then all this video is going to be linked. This slideshow is going to be linked in the daily lessons. You can always look there and rewrite it down if you want, if I go too fast or something. Okay, polynomial expressions. Here's an example of a polynomial. If you notice, the powers up here is 0 or greater. Okay, this is x to the 0. It's just the 6 here. But you can have constants, x to the first, x to the fourth. These are all individual terms that are separated by pluses and minuses. That's a polynomial. You should know that already. It's like a quadratic, only you have other powers besides 2. You have the third, fourth, fifth, and so on, infinitely many. Okay, polynomials right here. It says all exponents 0, 1, 2, 3, 4, 5, whatever. You can't have negatives. You can't have decimals. So it says here not a polynomial. It's 3x to the negative 3xy to the negative 1. That's why it's not a polynomial. You can't divide with polynomials. You can divide with rationals, though. That's what we're going over today. And then this one right here, it's x to the negative 3. So those are not polynomials. And so when I say polynomial, that's what I want to envision, want you to envision in your head. It's a bunch of terms that you're adding together, and the powers are 0, 1, 2, 3, or whatever, so on. Okay, rational expressions are the ratio. That's why it has rational in there. It's not like a rational, like rational means like usually it makes sense, it's logical. In this case, it does not mean that. It just means it's a ratio. So really they should be called like ratio expressions, but it's a ratio of 2 polynomials. So you're taking one polynomial like x squared plus 4, and you're dividing it by another polynomial, which is x minus 3. That's what a rational expression is. So we're just going a little bit further in our past understanding of polynomials, so now we're dividing them. And there's interesting things that happen when you divide. All right, rational graphs, the first thing we're going over, 3.1, is asymptotes. Okay, an asymptote, if you notice, it's this dashed line right here. It's essentially a line that when you create it, it's getting infinitesimally closer to some point of the graph as it goes to infinity. So if you notice this graph right here, it's going to infinity. It's getting infinitesimally closer here, but never actually touching it. And then this way as well, it's a negative infinity. It's getting infinitesimally closer without actually touching it. Okay, we are dealing with 2 flavors of these lines. We're doing vertical and we're doing horizontal. We are not doing a slant asymptote. That's what this is called, a slant asymptote. It's way harder to do, and we're just not dealing with it because it's an honors thing. If you were an honors advanced, you would find that slant asymptote there. But we are going to be dealing with vertical asymptotes, which is just a line up and down. Way easier to deal with. Okay, if you notice this line, it's vertical. It's getting infinitesimally closer right here, but never reaching it. And then if you go down here, it's also getting infinitesimally closer, but not reaching it. Okay. Asymptotes happen when you take a non-zero number. So just think of any number that's not 0. 1, 2, 3, 4, any number, negative a million, it doesn't matter. If you try to divide it by 0, this is what happens. Okay. And it's part of the reason why people say, if you divide by 0, you go to infinity. Okay, it's kind of right when you think that if you divide by 0, you go to infinity, but you could also go to negative infinity as well. Okay, if you notice, this one's going to infinity on both sides. This one's going to infinity here, and then negative infinity here. But anytime you try to divide by 0, this is what happens. You get a vertical asymptote. Okay, any questions so far of what I'm talking about? I just want your brains right now. You've seen vertical asymptotes before. We're just doing, I don't know, we're not really doing a deeper dive into what you've seen already. It's just we're covering it again because there's a lot of overlap with all these maths. You guys have done vertical asymptotes in intermediate algebra, right? Okay. Now, if you forgot, that's okay. I'm going to reteach it like you've never seen it before. So if you're thinking that I'm going to expect you to know this already, I'm not. All right, don't write this down, but a vertical asymptote is some x value, so x equals c. And if you plugged in c, if you were approaching c right here, your y is either going to infinity or negative infinity. Now, I would ignore all of this and just think about the graph. If you notice at this x value right here, it's a vertical line. This is going to infinity. The y's are both going to infinity. Okay, here the y is going to infinity or negative infinity. That's where a vertical asymptote happens. The y is going to negative infinity or positive infinity or both. Okay, that's what this says basically. X is equal to c is a vertical asymptote if, as x approaches some value, it goes to infinity, and or if you approach some value, it goes to negative. Okay. Vertical asymptotes happen when you divide by 0. I already talked about that. So it says vertical asymptotes occur at x values that cause a rational function to evaluate to a non-zero divided by 0. So 3 over 0, 2 over 0, 4 over 0, negative a million over 0. Doesn't matter what it is as long as it's not 0 over 0. 0 over 0 is a whole nother thing that we're going to go over in a second. Okay, so look at this right here, this f of x equation. It's 3 over x minus 1. And it says, what x value would cause f of x to be non-zero over 0? So what value would I have to plug in for x here to get a division by 0? Anybody? What would cause this bottom part to be equal to 0? If x was what? Negative. Not negative 1, just 1. 1 minus 1 is 0. So the formula for the vertical asymptote is x equals 1. I actually drew the graph right here, and it says 1 right here. So that asymptote is happening at x equals 1. That's essentially what you're going to be doing in this section. Is you're going to be setting the denominator, whoops, I don't know how to spell Desmos. You're going to be setting the denominator equal to 0 and solving. Okay, so we have some function f of x is equal to 3 divided by x minus 1. Okay, well, if you plugged in if you plugged in x here as 1, you would have 3 over 0. And I said, anytime you do 3 over 0, you're going to get an undefined. But if you actually tried to graph it, you'll see that it goes to either positive infinity all the way up here forever, or negative infinity all the way down here. That's how you know it's an asymptote. If I zoom out, you'll see it goes up and down forever. Okay, positive and negative infinity. That's the whole basis of what an asymptote is. It's what happens when you divide by 0. So if I did f of 1, it's going to say undefined because I'm plugging in, I'm plugging in 1 to this equation. It's 3 over 0. Now, any other value that I plug in, it would totally work. So say I plugged in 3. Now I have a value, 1.5. Okay, say I plugged in 2. Say I plugged in negative 1. Say I plugged in 0. Okay, because you're not dividing by a 0, it's just going to be a regular value. Okay. Now, you can't plug in 1, but what happens if I plug in a number like 0.9, which is pretty close to 1? Okay, 0.9 is approaching from this side as I go down here this way. Okay, but what happens if I plug in 0.99? That's even closer to 1. What happens if I plug in 0.999 repeating? What do you notice my f is going to? Oops, I just overloaded Desmos. But what do you notice? Where's this going? What's the trend? 0.9, 0.99? Where's that going? Anybody? A negatively bigger and bigger number. What's negative a bigger and bigger number? Negative infinity. Okay, if you notice the graph, if I'm going from 0.99, this side right here, it's going to negative infinity. So that kind of makes sense. Okay, what if I was going the other way now? Okay, what about 1.1? I'm going to put a bunch of zeros in here. So it's getting infinitesimally closer to 1, but never actually reaching it. If you notice, I'm going to positive infinity this time. So I overload the memory of Desmos. So this is going up this way. If you notice, it's going up to infinity if I get closer to 1 on the other side. So that's what vertical asymptotes are basically all about. You're just solving, it's basically this question right here is what you're going to be doing with the problems. You're setting the denominator equal to 0, and you're making sure the top is not equal to 0. Now, if the top is 0, if it's 0 over 0, that's called a hole. Okay, anytime you have a 0 over 0, it just doesn't exist in the graph, but there's no asymptote. So if you notice this example right here, it says f of x is equal to x minus 1 over x plus 3. If you plug 1 into the top and the bottom, you get 0 over 0. And if you notice right here, there's a hole at that point. There's still an asymptote at negative 3 right here. right here at -3, but there's a hole right here at 1 because it causes a 0 over 0. If you have 0 over 0, it's not an asymptote, it's a hole. Okay? Super important to understand. What I'm going to do is actually graph this one in Desmo so you can kind of see what it looks like. So we're going to do x plus 3, x minus 1 divided by x minus 1. Oops, that's not how it is. Okay, so the graph looks something like this. Let's get rid of this here. Now, if you notice, it doesn't actually show the hole at x equals 1, but if you put the mouse over it, it does. So right here, it shows that it's a hole. Okay, but the values on either side of it do exist. So if you go straight at 1, undefined, but if you go a little bit to this way, a little bit to this way, it does work. It's just when it's exactly equal to 1, it's a hole. Now, if you notice this problem right here, it has a hole at 1 because it would cause it 0 over 0, but this x plus 3, if you plugged in -3, you would have 0 on the bottom. So if you notice right here, there is still an asymptote at x equals -3. X equals -3. Graph it right on there. Okay. But x equals 1, there's not an asymptote, but there is a hole. Okay, you can't have asymptotes and holes in the same problem. Any questions on that? A non-zero over 0 is the big thing here with asymptotes. When you divide by 0, you go to infinity or -infinity. Okay, horizontal asymptotes are way easier than vertical asymptotes, thankfully, because you're dealing with x going to infinity. So horizontal asymptotes look like this. They're going left to right. If you notice, the same rule applies, though. It's getting infinitesimally closer here. The red and the blue are going to meet. They're getting infinitesimally closer to meet, but never actually meeting. And then over here, the blue and the red are getting infinitesimally closer again, but never actually meeting. In order to solve these, though, I do have to teach you a new concept, which is it's closely related to stuff that you're going to learn in calculus. So if you are planning on taking calculus, you're going to have a little bit of a head start here, because I'm going to show you something that's related to that so it can help you find these horizontal asymptotes. So it says right here, limits can be used to find horizontal asymptotes. Limits are basically things where you can't plug in infinity to a number. It's not into an equation. It's not a number that you can just plug in like 1, 2, or 3. But what you can do is use limits to have x approach infinity. So if you notice these right here, it says x is approaching infinity. So that means x is getting closer and closer to infinity, but never actually reaching it. Okay, so if you've ever seen the movie Toy Story, Buzz Lightyear says to infinity and beyond. You can't actually get to infinity, let alone you can't get beyond it in a way, if you want to think of it that way. So that's what this means. You're going to infinity. You're never actually reaching it because you can't. Okay, you can also do it for -infinity. I would just do infinity, though, for this class, because there's never going to be anything where you need -infinity for this class. Okay, so it says right here, it is a horizontal asymptote when as x goes to infinity or -infinity. Here it's going to infinity. If you notice, it's getting infinitesimally closer to it. It approaches some constant. Okay. Now, I said before that we're not going to be dealing with slant asymptotes. If you notice, this one is not going to, it's not horizontal, it's not vertical, it's both. It's a slant. We're not dealing with that. So we're only dealing it when it flatlines like this, or when it flatlines up and down. Okay. Let's do an example problem. So now I'm going to actually want you to write this down, because we're going to do some example problems involving asymptotes. And this is what your homework is going to be on too, is what I'm about to show you. It's just a bunch of example problems, and you have to find the vertical asymptote for it and the horizontal asymptote for it. So we're going to do, let's do f of x is equal to, let's do x squared minus 1 over 3x squared minus x. Okay. And for this problem, I want the vertical asymptotes and I want the horizontal asymptotes. Okay. Okay, if you remember before, I said vertical asymptotes occur when you have a non-zero over 0. Okay, so we need to figure out something that's non-zero over 0. So essentially what you need to do is look at, when is this equal to 0? Because that's where we're dividing by 0. So we're going to solve this to 0. So to find vertical asymptotes, that's step 1. set the denominator equal to 0, and solve. Okay, hopefully you know how to solve this. If you want, you can use quadratic formula, but it's way easier just to factor it. We're going to factor out an x, and you get 3x minus 1 is equal to 0. Okay. We're going to solve each of these. So we're going to do the x equal to 0, and we're going to do the 3x minus 1 equal to 0. Okay, the x equals 0 is already solved. We're going to add the 1 to both sides here, and you should get x is equal to 1/3 for this one. Okay, so these are possible vertical asymptotes, but you have to make sure that if you plug these into the top that you don't get 0. So if I plugged in 0 to the top, you get -1. So that's one of our vertical asymptotes. That one works. Okay, if you plug 1/3 in the top, you definitely are not going to get 0 as well. So technically you have two vertical asymptotes here, 0 and 1/3. Okay, so let's actually look at what this looks like when we graph it, just to make sure we're doing this right. So it's going to be x squared minus 1 over 3x squared, what was it? Minus x. Oops. Should get something like that. Okay. Now we had, well, these are too close together. Hold on one second. Let's bring this down and do this. Okay. Now we had x is equal to 0 as one of the asymptotes and x is equal to 1/3 as one of the asymptotes. So what I'm going to do here is I'm actually going to graph these and I'll make them a dashed line. And let's do a dashed line like that. And then we'll do one for this one as well. Dashed line. And you can see that they are both asymptotes for this graph. I can get rid of the grid here. Let's get rid of this as well, so it's a little bit easier to see. And you can see that x equals 0 and x equals 1/3 is technically an asymptote for this graph. Okay. So moral of the story is set the denominator equal to 0, solve, and then make sure it's not a 0 over 0, which sometimes it will be. That would be a hole if that was happening. All right, now we need to figure out what the horizontal asymptote is for this. And to do that, we're going to use limits. So what you need to do is write the limit, that just means LIM, as x approaches infinity of whatever f of x is. In this case, it's x squared minus 1 over 3x squared minus x. All right, this is going to get really crazy, so make sure you pay attention because this is completely new now. So what you can do here is x is approaching infinity. Okay, it's kind of like saying x equals infinity, but again, you can't actually equal infinity. So that's why it says the x is approaching infinity. Because you can, if you think about it, if x is approaching infinity, that means it's infinity squared minus 1. Okay, now because we're going to infinity, we can do this really cool thing with math is we can just get rid of this minus 1 because it's meaningless. It's like if you had $1 billion trillion and you lost a penny. Okay, only even less than that because you're going to infinity. $1 billion trillion is a finite number, but imagine infinitely many dollars and you lose a penny. Okay, so we can actually get rid of this, which is really kind of weird to think about because we're not used to doing that kind of thing. But we can get rid of that constant. It's a 1. This x is infinity, that x is infinity, that x is infinity. You can't get rid of infinity. Okay, but you can get rid of a 1 because it's just 1. It's, oops, I didn't want to do that. It's just basic. It doesn't change with infinity. So we're just going to get rid of it. Now, this makes the math a lot easier that we can do here. Check this out. What you can do is you can divide the top by x. So you're just going to have an x here. Divide the bottom by x. So that x goes away and this becomes a 1. So I divided the top and the bottom by x. Okay. Let me rewrite this because this might make more sense if I rewrite it rather than trying to throw it all in one problem. So I'm going to rewrite it here. This is going to be x times x on the top. And then on the bottom, I'm going to factor out an x. And you get 3x minus 1 times x. Now, if you notice, this x and this x will cancel out. So x over x, which is legal. Infinity over infinity is technically, will cancel out as long as they're equal infinities. In this case, they are equal infinities. Now what we can do, check this out, is I can get rid of this 1 again because it's meaningless. X is still going to infinity. And now you end up with x over 3x. So x over x cancels, and you're left with 1/3. Well, that's what your horizontal asymptote is. X equals 1/3. Now that is completely unrelated to the vertical asymptote at 1/3, because honestly, I made up this problem and I'm surprised it worked out to be both 1/3. Usually they're not the same number, so don't assume that they are. And this is essentially all of section 3.1. It's finding vertical asymptotes and finding horizontal asymptotes. And the main thing is that's new is the limit as x goes to infinity. But wouldn't it be cool if there was a shortcut that we can do? Let me show you the shortcut, so you don't have to do all that stuff I just did. Check this out. If we're going to infinity on this, all you have to look at is the x squared, the leading term. If you wanted, you can get rid of this and get rid of this. X squared over x squared cancels, and you're left with 1. Whoops, you're left with 1/3. So if you want, you can look for just the leading term for each of these, get rid of those right away, and you'll still end up with the same answer. Okay, and I will still give you full credit. You don't necessarily need to use the limit notation. But I did want to show you where that comes from, just in case you, I don't know, see it again. Okay, any questions on what I did here? Okay, let's do another one. Let's do f of x is equal to, let's do 4x squared minus x plus 1 divided by x plus 5. All right, just like before, I want the vertical asymptote and I want the horizontal asymptote. Okay. For the vertical asymptote, again, all you do is you take whatever's down here and you set it equal to 0, and you solve. So you should get x is equal to -5. Now, you make sure that if you plug in -5 to the top that you don't get 0. You don't, and you can just kind of see that it wouldn't come out to be a 0 if you plugged in -5. So that's technically our answer for the vertical asymptote. Oh shoot, I forgot to show you something about this last problem. I forgot to show you that it was actually 1/3 for the y. So check this out. I'm going to graph y equals 1/3. And if you notice, here, let me dash that. Let's do orange and dashed. If you notice, it looks like it actually intersects it, but if you zoomed in here, you'll see that it is still separated. Okay. Now, if you zoomed out further and went further down to infinity and you zoomed in, eventually you'd still see that it's separated by a little bit. Okay. Let you get the idea. Okay, let's see here. All right, going back to this one. This one is -5, and let me just check it really quick by throwing in the calculator. So we have 4x squared minus x minus 1. Oops, plus 1. And then we're doing x plus 5 here. Get rid of this and this and this. We'll bring back our grid. Okay, x equals -5 is where the asymptote supposedly happens. So let's check that out. X equals -5. We'll graph it right there. It's hard to see because it's technically going to infinity and it just climbs so fast. But if we do this, you could see the rest of the graph, and you can see that -5 is the vertical asymptote for it. And it works out perfectly. Now we need to do the horizontal asymptote. With the horizontal asymptote, again, I said you can just look at the leading terms for each of these. So we have 4x squared minus x plus 1 divided by x plus 5. You dropped your wallet, dude. Yeah, I don't trust Scott. I know, I'm just saying I didn't trust you to go. I felt like you would have just stole his wallet there. Scott, I'm just joking, dude. See, there you go. All right, so what you need to do for this is just look at the leading term. We're going to infinity for x, so we can get rid of all this, and we can get rid of all this. Okay? If you don't believe me, you can use limits. You'll see that the same thing happens, but I'm just showing you the shortcut. Divide the top and the bottom by x, and you're left with 4x. But if you remember, we have the limit as x is going to infinity. If x goes to infinity, what's 4 times x? 4 times infinity, which is infinity. So your answer for this one is going to be infinity. And I told you before that your horizontal asymptote has to be a specific value. So if you ever get infinity like this, that means there is no horizontal asymptote. Okay, it's called a slant asymptote. I'm going to show you that it goes slant. But if it's going to infinity, it's not going to a specific value. Okay, the other one was going to a specific value if you look at the graph. Oh, I already deleted the other one, but it was going closer and closer to 1/3. This one, if you reset the zoom on it, you'll notice that it actually goes to infinity. It's not flatlining anywhere. Okay, that graph is going up forever. If you wanted to, this is what infinity looks like in your calculator. If you just put a 1 in here and then just add a 0 and then another 0, oops, another 0, another 0, you'll notice it's going to infinity. Eventually it overloads Desmos if I add enough zeros here, because there's only so much memory allocation that they allow on this. Otherwise you could do like a DDoS attack on this website. So they limit it. Oh man, that's embarrassing. You know why though? Because it offloaded the memory to just understanding that number and the power. So it doesn't need to worry about all the other the other decimal places. That's why. It doesn't matter what I'm saying right now. But let's do, yeah, so this is just us going to infinity. It doesn't go to a specific value. But check this out. If I change this to an x squared, now the power on the top and the power on the bottom are the same. So you can get the x squareds cancel. You end up just going to 4. Okay, let me show you that it's going to 4 here. It kind of shows it right there. But watch this. If you're going, it kind of already gives it away, but if you do f of 1, it's 2/3. But watch this, 10, 100. You notice it's not going to infinity anymore. It's getting infinitesimally closer to 4. If you overload Desmos now, it'll just put 4 in. Even though it's really 3.999 repeating, it just rounded it off. Okay, that's because I made it an x squared here. The original problem that I just gave you, it was just an x. So moral of the story, I would write this down. If the power on top is bigger, there's no horizontal asymptote. Okay, I'm going to write that down. But if the power on top is bigger, if the degree on top is bigger, if the degree of the numerator is greater than the denominator, there's no horizontal asymptote. Then there's no horizontal asymptote. By the way, you can write HA and VA on your tests when you're looking for this stuff. I will know what you mean. Okay. If the degree of the numerator and the denominator are equal, then there is a horizontal asymptote. Okay. So this one's if it's greater than the other. The other one is if it's equal, there is a horizontal asymptote, just like the first one we did. But what happens if the denominator had a bigger degree? Does anybody know that? Does anybody want to guess if the degree on the bottom is bigger? All right, well, let's do a problem and then we'll try to figure it out here. All right, so let's do f of x is equal to, let's just put x minus 1 on top here. And at the bottom, let's do x plus 3 times x minus 2. Okay. The degree on the bottom is 2. The degree on the top is 1 because there's only one x on top and there's 2 x's on the bottom. If you multiply them together, you get x squared. All right, so let's find the vertical asymptote and the horizontal asymptote. Okay, right away, what are the vertical asymptotes? You should be able to do this pretty quickly because it's already in factored form. X equals what? So yell it out. -3 and 2. Okay, would cause this to be 0, would cause this to be 0. You can't divide by 0. If you put -3 up top, it's not 0. If you put a 2 up top, it's not 0. So the vertical asymptotes are -3 and 2. Okay. But let's try to figure out the horizontal asymptote now. So we have x. This is where the limits really come in handy here. You have x minus 1 over x plus 3 times x minus 2. But if you remember before, constants are meaningless when we're dealing with infinity. Okay, and this one we are dealing with infinity. So check this out. I can get rid of this 1 this 3, and this 2. Okay, let's keep going here. Divide this by x and this by x, you get 1. And now you're left with 1 over x. And x is approaching infinity. So what is 1 divided by infinity? Does anybody have any ideas? 1 divided by infinity. If you had 1 pizza and you were dividing it by infinitely many people, how much pizza does each person get? Basically what? Infinitely many, even though there's just 1 pizza? Well, they would all get 1, but what does each one get? All right, let's follow a pattern here, since we're going to infinity. What? Thank you. 0. Okay, let's think about it this way. If you had 1 pizza and you divided it by 1 person, that 1 person gets 1 pizza, right? What happens if you took that one pizza and divided it by 10 people? They could each get 0.1 pizzas, right? But what happens if you divide it by 100? What happens if you divide it by 1,000? We're not even close to infinity right now because we'll never be close to infinity. But do you notice the trend here? Where is this number going to? 0. It's getting closer and closer to 0. So, moral of the story, if the degree on the bottom is bigger, your vertical asymptote, I'm sorry, your horizontal asymptote is y equals 0. Okay, let's graph this out to see what it looks like. So we have x minus 1, and then x plus 3, x minus 2. Okay, first let's check the vertical asymptotes. So x equals -3 and 2. Let's get rid of this. Let's make this a dashed line here. And if you notice, at -3, which is right here, and 2, we have vertical asymptotes. Awesome. But the horizontal asymptote, where is this going? Where is this getting infinitesimally closer to? Anybody? 0. Okay. Another way you can do this is if you did f of 1, and then let's do 10. Okay, 0.0865. Okay, let's do 100. Uh-oh, where's this trending to? It's basically trending to 0. Okay, that's where it's going. And it never will be 0, because if you had 1 pizza and you were dividing it by infinitely many people, technically it's not 0 pizzas. But if you really break it down, if you kept dividing pizza up, you would eventually get to the atoms, and then smaller than atoms. And as soon as you get to the atoms, you're not really a pizza anymore, obviously, because pizza is made of molecules, if you've taken chemistry before. But it's cool to think about infinity, even though it doesn't work in real life, because there's always limits in real life.